This is a modern game development workstation. No massive desktop tower, no jet engine fans, and no thick cables tangling under your feet. Just a laptop remoting into a massive pool of hardware down the hall. Right now, the clean setup has access to more raw rendering and compute power than the traditional desktop rigs that used to take up half the desk. A little while ago, an indie game studio came to ServerMonkey with a massive bottleneck. They were scaling up the development, but renting cloud GPUs for automated testing and running AI models was on track to burn a massive hole in their monthly budget. Their question to us was simple. Can you build us an on-premise enterprise piece that handles our backend testing and local AI, but without the $10,000 enterprise GPU price tag? So we did. This is the Dell PowerEdge R7525 that's running on two RTX 5060s. You might be wondering, how are the GPUs not sticking off the server? Because they're low profile. For those that don't know, if you've ever dropped a standard desktop graphics card into a 2U server, it's a nightmare. The top mounted power cables stick out, so the serverlet will never really close. But if it's a low profile graphics card, it works. And plus, game studios don't need overpriced data center GPUs to test mainstream games because most of their players aren't running them. That's why developers need mid-range consumer hardware like these Blackwell cards to see exactly what the end user experiences. But dropping consumer cards into a 2U enterprise chassis comes with a dangerous engineering hurdle. Standard server 8-pin cables are EPS CPU power, which has a completely inverted voltage layout compared to consumer PCIe 8-pin cables. They look identical, but if you just grab a standard server cable and force it in there, you send 12 volts straight into the GPU's ground lanes and instantly frying the new graphics card. So to make this work safely, we use dedicated Dell breakout cables to map the motherboard's proprietary headers to the consumer PCIe pinout. Then there's the battle of the fans. Enterprise servers are designed for linear front-to-back airflow using high static pressure chassis fans. Consumer cards, however, use active axial fans that pull air from the side and dump it inside the case. In a tight 2U chassis, these two cooling styles can fight each other. Fortunately, the brute force airflow from the Dell chassis completely floods the PCIe zone with fresh air, keeping the 5060s cool under load. The real challenge is iDRAC. The moment Dell's management controller detects uncertified consumer GPUs, its safety default is to ramp the server fans to 100%, turning the machine into a literal jet engine. To solve this, we didn't even need to dive into complex command line hacks. We just hopped straight into iDRAC and adjust the thermal settings directly in the web GUI. We override the automatic third-party PCIe fan panic, and that keeps the baseline system whisper quiet, allowing the chassis to dynamically ramp up airflow only when the NVIDIA drivers report that the cards are actually working hard. So how does a game studio test games on a server with no monitor or remote desktop GUI? Well, they don't need to anymore. And this is because modern games nowadays are tested using headless, automated CI/CD pipelines. These studios' developers don't use parsec or controllers here. And because we're operating entirely within an Ubuntu server ecosystem as well, we don't even need a physical monitor hooked up to that to test code. This functions as a centralized headless QA node. So when a developer commits a game update to the master branch, our background CI/CD pipeline automatically pushes the build straight to this machine. Using Linux virtual display drivers, the game engine launches headlessly in the background. Automated bots run through the map, logging performance metrics and caching regressions on the hardware real players actually own. In other words, the game runs entirely on system memory. The RTX 5060s chew through the physics, collision boundaries, and game mechanics at completely uncapped frame rates to find bugs as fast as humanly possible. No pixels are ever drawn to a screen. It is pure raw data processing. But what happens when a headless test crashes? You get a massive unreadable text file log. And to handle that triage safely and locally, the studio uses the Duo 5060s to host a completely private on-premise LLM. In this case, we're using OpenWebUI and Qwen 2.5. See, the Qwen model requires roughly 10 gigabytes of VRAM headroom, but a single RTX 5060 only has 8 gigabytes. So watch what happens the second we initialize the model. Let me paste in that example prompt. Okay. Boom. As you can see, the server automatically splits the AI's memory footprint, perfectly across the physical cards. The exact millisecond the AI begins thinking and outputting the code, the power consumption violently spikes, pinning both cards right up to their maximum power limits. The Blackwell Tensor cores are firing at 100% capacity, splitting the computational workload cleanly down the middle across our budget cards. Best of all, there's zero risk of leaking proprietary source code or unreleased game IP to public cloud API. But where though? Building a streaming server on regular gaming graphics cards is a headache. NVIDIA caps how many video streams each card can run, and it won't let you share one card across multiple machines, and technically bans them from data centers anyway. They want you buying the expensive data center cards instead. But for a modern headless automation factory running local AI models and automated code runners, the dual low-profile RTX 5060 config here completely bypasses the traditional virtualization logs. By using lightweight containers, the studio can run multiple automated tests simultaneously, making this server an isolated 100% secure offline development pipeline that protects their IP and eliminates their cloud bill forever. It's the ultimate footprint cheat code for an indie game studio looking to scale. Thank you for tuning into ServerMonkey, and I'll see you in the next one.